All right, everyone, we are going to get started, including the good folks in the overflow area. We are going to have Todd Gureckis, professor of psychology at New York University.
Great. Thanks for having me part of this. This is a really great workshop, and it relates to a lot of ideas that I've been interested in thinking about. I don't know that I've worked as much on actually contributing to the AI efficiency story, but maybe some things that I have worked on will spark some conversation and discussion along those lines. So yeah, I was going to talk about computational constraints on discovery. And first I was going to just start off with the recognition that I think has already been made a little bit in the presentations so far about measuring costs of intelligence, basically. So I'm somewhat involved with this ArcPrize competition, which many people may have heard of. So ArcPrize is a challenge task that was created by Francois Chollet several years ago. And what it is a program induction task where people have to see input-output examples. So you see like a training set of a bunch of input-outputs of a potential program. So you can think of like an input is then run through a program, and then it creates an output. You see a couple few-shot examples of inputs translated into their outputs, and then you have to try to guess what you think the underlying rule is in that case, and complete the pattern in that case. And so you can like look here and think a rule like extend the extensions of the things, and then you would know how to answer the next question or whatever. And so this puzzle was immediately interesting to me as a cognitive science. It looks like an intelligence task. It's super interesting to kind of study it. But it attracted a huge amount of attention actually from like the AI community, to the point where at one point I thought it was just like a bespoke kind of benchmark, and then you see like it being like the major thing that OpenAI puts in their presentations to talk about how good their model's doing is like how well it does on the ArcPrize challenge. And part of the reason is that it's a challenge that's designed to resist benchmark saturation in various ways. One of the ways is that there's a test set that's like hidden away in a drawer that's only available to the runners of the prize, and so you can't sort of get access to these like special evaluation tests, and so you sort of don't know what's on the test ever, even if you can get lots of examples or even make synthetic examples. And they've even offered now like $1 million, I think it's up to $2 million now, for a prize that can succeed at matching human performance in the task, which is relatively high actually. Now, one of the things I think is actually really interesting about it is that the ArcPrize is framed in such a way that there's actually a compute cap on what consists of a valid solution to the problem. So nobody's actually won the $1 million prize at this point, or the $2 million prize, in part because while people have succeeded at getting close to human level performance at the task itself, they've used more compute than is allowed by the rules of the task. So there's essentially a compute ceiling that you have to fall under. There's different versions of the task. There's a Kaggle task where you have to use 42 cents per task of compute. There's a leaderboard task where you can have more. There's a human panel where they estimated various ways of computing it because they sort of give people a big bonus to come into the lab as well as like some bonus per problem. But something around $5 per task is what they basically are paying human subjects to do the task. And then you can see that there was a big news story that came out like when OpenAI's O3 model came out, and it like sort of blasted the benchmark out of the water the first time that anybody exceeded human performance, getting close to like 88% at the task. But what was interesting is that the O3 algorithm spent about $4,000 per task, per problem, to solve the solution. And so I did some conversation with Claude to try to figure out exactly how much power that would be. It's not that easy to figure out, like, you know, if you spend that much compute, how much is it really electricity and whatever, energy, but like the energy costs roughly worked out to be something like 6,000 kilowatt hours. Would you ever looked at your bill? My house like uses like 1 kilowatt hour or something like that, so it's like in a month. So like this is like roughly like 6 or 7 months of household electricity to solve one of these problems. And meanwhile, human brain, right? We run on whatever people say 20 watts or whatever. We do it for 10 minutes. So there's a factor of like 10 to the 6 energy ratio difference between a human solving this task and the best in class of the AI systems or whatever. And it's not just Arc that's done that. Like actually looking around, there's like increasingly compute budgets that are being set for AI challenges in terms of, with like a lot of different non-alignable ways of doing that. Like sort of like, like there would be things like caps on amount of money, time to train, like the number of GPUs you can use, for how long you can use them, right, all act as constraints for considering successful solutions within AI benchmarks and robotics as well. But cognitive science, as other people have said, still evaluates models as if compute were actually not a constraint, right? Like, so what we typically ask of our models are things like, does it fit the behavioral data, right? So we get a fit statistic. We ask if it's parsimonious, if it could be explained by a simpler model by fitting, AIC or BIC or whatever. We ask things like, is our model interpretable or biologically plausible? We rarely ask if like the brain could actually afford to run the algorithm, what it would cost in time, energy, and working memory and so forth, and does it scale beyond what are often the toy problems that we use in experiments where we have relatively limited number of stimuli and stuff like that, and we have to go out into the real world where there's potentially thousands or millions of categories and stimuli that we need to learn about. So there is one framework that does take this, I think, somewhat seriously, which is the resource rational argument from Leader and Griffiths. And the idea in this, for people who aren't familiar, is that it is the idea that maybe people aren't optimal at any particular task that they perform, but that they're optimal given some constraints. And the constraints are things like cognitive limitations that have to do with amount of time they can think before they have to make a decision, the amount of memory they can use in a particular problem, and things like that. And it's usually expressed as some kind of trade-off where there's some strategy or policy that you could perform in the world, and you can imagine an expected utility of performing that action. Or that policy, and then you sort of subtract off some cost of running that algorithm in some sense. And so then at some point we now have a meta-learning problem of trying to figure out which algorithm should we pick from the set of possible solutions to the problem that balance these costs in a way that enable us to do good performance while not expending too much cost. So an illustrative example of that, Fred Callaway has a really interesting paper talking about planning problems, where there's their sequential decision-making problem, thinking about thinking. So you're thinking about how to plan a future route to a destination or a goal. There's different planning algorithms that have been proposed by people about how people might do that heuristically. But they propose a kind of a thing they call the meta MDP, which is a resource rational approach for trying to come up with optimal ways of planning, subject to a constraint that has to do with memory and the complexity of the policy that you maintain. And they show that across a lot of experiments that people's behavior varies from one task to the next in a very interesting and systematic way in the sense of their observable planning behavior, and that they're sensitive to things like the cost of the task as well as the resource demands of the task that they're presented with. So sort of the cost meaning how much they're rewarded for doing the task, as well as how difficult the task is to do or represent. Right. And there's plenty of examples of this in the literature in behavioral econ and things like that, where people have looked at how incentives and rewards change cognitive performance at various kinds of tasks. So here's an example from my colleague at NYU, Andrew Kaplan, who's an economist, who had people do this task where they have to look at a screen full of polygons, and they have to count how many six-sided figures are there, and is there more six-sided than, say, four-sided objects or something like that? So that's the task you have to do, okay, and report that correctly. And you get paid if you're correct. And so then across different tasks, they change the incentive to make it more valuable for you to perform correctly at the task. And people's accuracy sort of looks like this demand curve where they sort of if you get paid more to do the task, you'll execute the cognitive strategy behind actually doing the task of counting the shapes better than if you weren't paid. And furthermore, there's a little difference here because of the task difficulty. So they varied. Was it a very easy task? There was only a few, and so you could tell, or it was a hard task where it was 8-sided objects versus 7-sided objects or something like that. And you would really have to go and count to actually do the task or whatever. And so you get these beautiful demand curves that show that the amount of we might think of it as compute that the people will apply to the problem scales with the magnitude of the reward that they are being offered in doing the task or whatever. Okay, so so then it gives me to the story. I'm going to have a little bit of a story for this talk, a little bit how I got to this thing. So I saw a workshop where Andrew presented this work, and I was that's really weird because many years ago when we first started doing research on Mechanical Turk online, we were worried that our subjects weren't replicating basic laboratory phenomena that we had seen before. And so we thought maybe we weren't paying them enough. And so we did a couple titration experiments where we would vary the pay on Mechanical Turk for the same task, seeing if because we weren't getting task behavior that we normally saw, we were like, if we pay people more, will we eventually get them to do better, right? And one of the things that we saw in that was that nothing happened actually. Like as we paid people more, they didn't do better at the tasks that we expected. And we sort of filed it away. It turned out that the narrative of the paper that we wrote about that was actually like, hey, actually, like instructions and telling people what the task is way more important than how much you pay them. If they don't understand what they're supposed to do and they come in with the wrong assumptions, that matter more than the pay. But not that we discounted pay, but it was just stuck in my mind that it was a little bit weird that we had order of magnitude of 10 times pay and we didn't see a single change in performance. And I was sort of curious how they see these patterns everywhere. So we were interested in this task that's been studied quite a lot. It's a little bit of a boring task now because people have studied it so much, but on the other hand, it has a really high replicability quotient, in the sense that hundreds of people have basically done this experiment independently and have gotten the same general results. And so it's a very good kind of litmus test to kind of stand on to look at performance and things. So the task, if people aren't familiar, it's called it's SHJ, but it stands for Shepard, Hovland, Jenkins. It's a paper from 1962. And it's kind of a beautiful design in the sense that there are subjects in these experiments were given a set of 8 shapes. These are triangles, so each of these boxes contains 8 shapes, as you can see. They're all the same 8 shapes. And the things are grouped into categories, so either category A or category B. And it's the same 8 items just arranged into a category in a different way. So one of them will be called the type 1 category, and it's a category where one feature matters. So if something's black, it's in category A. If it's in white, it's in category B. Right? And so that's just the category rule that the subject has to learn through the task. And then you can have the same set of items can be shuffled around between the rows and columns, right? And make different categorizations. So here's one that's called the type 2 problem, and it's kind of like an XOR relationship over the set of features. So everything on this column is A and this is B, and you have to kind of tell them apart. Okay. And so you get different ways of taking these same 8 items and just assigning them to categories. It has a dramatic effect on how difficult it is for people to learn them. So the first one is a really easy problem. You just have to pick up on one feature and figure it out. Whereas the type 6 pattern down here, if you look at it for a while, you might have difficulty. The common story is that there's no regularity really, and that you have to basically memorize the labels that go with each example. And that itself is actually an interesting fact because you, in theory, could learn to memorize all the examples. And so it's the fact that it's easier to learn this shows something about a cognitive operation of simplicity or something like that you're applying a rule or something more compact than just memorizing the associations between the stimuli and their labels. A very classic finding that people have is that you can show as people get exposed to repeated examples of those category members, they make fewer errors. And there's a curve that drops off as they get better. And they learn the type 1 pattern relatively quickly. They within just a couple trials, they're able to get 100% performance. Type 2 is a little bit harder. 3, 4, 5 kind of cluster together, and type 6 remains particularly difficult. So this is a classic study. So there's a sense in which, relating back to the title of the talk, I kind of think of this as it's definitely a learning task. It has an element of discovery in a way because there's an underlying pattern to the world that the subject is presented with, and they sort of have to discover what they think that rule is, right? And so it's you can think of the task as these learning curves as charting the process of discovering what it is, what the rule is that underlie these a set of examples. I guess then there's a kind of clean prediction, which actually hasn't really been tested with these types of stimuli before, which is that maybe rule discovery is some type of a resource rational kind of cognition, where if you increase the stakes of performing the task, that people would devote more computation to it, and whether that's attention or search and memory and things like that, that would make them perform better at the task, basically. So higher stakes should drive better discovery. So my student, Pam Osborne-Pop, and I and several collaborators created a version of the Shepard-Hovland-Jenkins task where we manipulated financial incentives between subjects sometimes and also within subjects. There's a whole bunch of experiments that we did. We tried different financial motivations for people. So one of the ones was that like as they went through the task and they issued responses, they would essentially be buying a lottery ticket into a system that was biased in a particular way. And so that the more correct answers they gave, they had more tickets to the lottery, basically, and so they had a better chance of winning. And also variations in magnitude of the reward. These are all things that behavioral econ people are very interested in, and about how utility influences the expectation. And I won't go into the details of that too much, but just to understand that the task was set up such a way that you're doing the classic category learning task, but you're in a condition where we can manipulate the stakes for you, where if you perform better, you can get more money, and across conditions, we can make that more or less lucrative for you. Now, the first pattern from I'm just going to summarize because there's like 5 or 6 experiments in and I don't need to go into all of them. But one of the things that's interesting about it is that we replicate, if we collapse across most of our conditions, we replicate the classic finding of rule type being difficulty. So the type 1 problem is generally easier than type 2. 3, 4, and 5 are kind of clustered together, and type 6 is harder. We kind of underpredict the type 2 phenomena relative to past studies, but that's actually been a phenomena that's also been understood in the field. That there's various hypotheses about it, but one of them is that we don't train people in logic anymore when they're a psych student. And so the XOR is a complicated logical rule that they might have had exposure to through school. And so the original papers that were done in like the 1960s up to the 80s might have had students who had been trained more in logical reasoning, and that's atrophied in some respects. But the interesting thing, but kind of fit with my expectation, was actually that like the incentive conditions had basically a flat effect. Like there was no detectable effect in our sample of like making people learn these things faster across low, medium, and high incentive. So like I said, I won't go through all the experiments, but we sort of the categories were pretty flat. Then we went back and tried. Okay, maybe we need to do it within subject, and so we did it within subject. It was still pretty flat. We tried doing like different kinds of like task manipulations. It still was pretty flat. We basically could never get a robust effect. Then we finally had reviewers who said, okay, you got to pre-register your design. You got to use Bayes factor to determine whether you can accept the null hypothesis. Highly powered design with a huge budget, $10,000 for this one experiment to get a huge sample to conclude that we could not detect an effect of incentive on this task. So just to say that I'm like somewhat confident, as much as I've ever been about something, that was very hard to change people's behavior on. Yeah. The highest incentive, they're not that high. Yeah, so I think in like some philosophical discussion, you could say, give you $1 million or something like that if you get it right, and then like maybe some people would shift. The problem with some of that stuff is that if you get into like really, really high amounts of money, you start getting people using external memory aids and stuff like that, like writing it down, right? And so if they use Claude or write a computer program themselves in order to help them solve the problem to get $1 million bonus, it's not really measuring the effect that we're interested in studying. So, but I think it was like it got up to like $10 of a bonus for like a 5-minute task or something like that. So it was a substantially higher pay rate than is typical on the online study platforms. Okay, so we had all these like null effects, and it would be a really boring talk if I just told you about null effects. So there's one thing that did work. So we did a variation of the task that was sort of similar to the Kaplan study. So if you remember the Kaplan study I showed you, the task was count how many polygons had a certain number of sides. So we made like a Shepard-Hovland-Jenkins version of that, where what people were shown was stimuli, a whole bag of stimuli that were from that design, and they were told a rule at the top. So triangle cards are in group A, square cards are in group B. So that's like the type 1 rule, like the single feature rule. They're told that rule, and they're supposed to do the same task, like count how many things are in A versus how many things are in B, and report which one has more. So they're doing the exact same task that Kaplan had them do, except for instead of using a pre-built category of polygon number counting, they were being given rules from this particular task, these logical rules, and they had to just like execute them. And that's one place we did find like relatively robust effects of incentives. So like if we take different rules that we gave people, different magnitudes of reward that we gave them, their performance profile looked similar to the profiles from Kaplan. And also you see this pattern in their reaction time, that they spend more time on the task they're more careful or whatever in order to like succeed when they have to just like actually follow the task. Now, it's also interesting though that there is a little bit of a difference between the rule types. So like different rules might be like differently complex to actually like execute. You know, like the type 1 rule is just like black versus white, but the more complicated rule could have conjunctions and disjunctions and stuff like that that might be difficult for them to cognitively deal with and might have affected performance as well. So I should go back one thing though and just say that like I think it's kind of interesting that the incentives didn't have an effect here, but that the original Shepard idea speaks really loudly in the data. So like the fact of rule complexity influencing behavior in this task really strongly comes through, whereas the incentives is kind of more of a mishmash if hard to detect at all, right? Which I think is actually interesting. Okay, so then we can think about like some models actually to like try to like explain this. And so other people were talking about, Tom was talking about like the rational rules model. It's a wonderful paper. I love this paper. It's one of the cleanest categorization papers I've ever seen. It replaced a model that previously had like 11 parameters with one that had 1, which was just a great success. So the idea is that there is like a space of rules that people have to learn and a set of examples, and they have labels for those examples, and then they kind of do a Bayesian inference. Not over, they do it over a hypothesis space that includes grammatical constructions, like symbolic grammatical instructions that are generated from this grammar. And it's just a simple disjunctive normal form grammar that can express lots of Boolean concepts, like, you know, A and B, and it's like the positive examples of the category. So like, you know, size and color makes you be an A or whatever, particular values of those features or whatever. That would be an example derivation that comes out of the grammar. And the prior was set such in a way that it sort of favors like sort of short and simple rules, which kind of gets the preference for kind of simple rules in the original Shepard design. And it roughly captures the Shepard difficulty ordering, although there's a little bit of difficulty with accounting for that type 2 pattern given that particular syntactic prior. But it's still a really beautiful paper. But it doesn't have a built-in notion of cost necessarily, so inference is kind of treated as free. There is like an approximation algorithm that is proposed in the model, but it's not tied to a particular kind of like cost analysis. The paper kind of predated a little bit of the ideas about resource rationality, I think. So you can make like a resource rational version of this rule learning model, basically. And so the model treats like inference as costly and tries to optimize like how much to compute. A typical way of doing that is to assume that like there's like a cognitive operation involved in like sampling a hypothesis, sort of. So you have like a different rule in mind, and sort of taking a sample from your that distribution has a cost associated with it. And so the idea is that then you can there's a cost. You can only take a certain number of samples. You can't use the full Bayesian posterior over that entire space. It's also infinite, so it's also another issue. But you know, so you take a small set of possible rules, and then you can make a prediction about the category label of a new item or whatever by sort of doing Bayesian model averaging over the set of samples that you took, maybe weighted by their posterior likelihood. And so you can make a meta-learning model sort of by just kind of re-expressing the decision of how many samples to take in terms of this kind of cost-benefit trade-off, where you have like a rule, a policy that you're going to follow, essentially how you're going to assign labels to categories, and you're going to like trade off between the potential reward for having a high accuracy rule with the cost of having estimated that with samples, and the optimal balance, the optimal budget then would kind of balance between the two, where if you set the cost really low, you would take many samples and you'd be closer to kind of like a Bayes optimal solution, and if you increase that cost, you would be more of an approximation in that case. And so that's the resource rational prediction. And so did a little simulation. A lot of these things, the simulations are going to show you weren't like necessarily like fit to data, but just more to get like kind of qualitative impressions of like the way the model works. So take the model and kind of like imagine how performance on the different Shepard-Hava and Jenkins tasks would change as I change the sample budget, like giving it more samples that it can average from, right? And you can see that sort of there's like unbounded posterior accuracy, and in a lot of ways, like as you get more and more samples, you get closer and closer to the full Bayesian solution, and eventually you can get like basically perfect performance at it. And you know, you can also compute kind of for any given cost, you can compute like what the optimal sample budget that you should probably take in order to maintain utility, right? So like how many samples should you take if you're kind of resource rational in that case? And you can see that it's like kind of on the order of like 10 to 20 samples in this particular paradigm when you average them that way. That like if you get around that many, then you can you'll optimize your performance, and it gets pretty close to the performance of the Shepard-Hoffman-Jenkins thing. But the main thing to point out is that as we adjust the rewards for the task, performance basically just goes up unendedly. So the model takes more samples, classification increases. It's still generally ordered by the difficulty of representing the prior in the model, but it doesn't seem to account for our results where we couldn't really move people with the incentives. And so I go to propose a different idea, I guess, a little bit along those lines of how one would actually account for it. So one idea, and I don't know that it's 100% right, but it's sort of somewhat a discussion point, is that idea generation is a little bit more difficult than evaluation. So the bottleneck maybe in rule learning and discovery is actually thinking about the hypothesis in the first place. And then there's an evaluation process, which is to check whether your idea is right. And so those two things are kind of separate. And possibly one of those is more susceptible to costs or something than the other one. You might even think of it as volitional or something like that, having more control. And so the idea you have an idea that bubbles up, and you don't maybe not have that control over whether you think of a good idea in a particular situation. But once you have an idea, you can kind of be diligent about verifying whether it's good. And there might be a cost-sensitive calculation that enters in there. So the new little toy model is still uses the same representational space as the rational rules model and the same prior, basically. It starts by sampling a rule from the complexity-weighted prior from the rational rules model. And then on each trial, it sees a stimulus, like the subjects do, and it applies the current rule and gets feedback. If it's correct, it records that example in memory, and then moves on. But if it makes an error, it triggers hypothesis revision. And this is inspired by a classic kind of model from Bauer and Trabasso around the same time as the Shepard-Hoffman-Jenkins thing about one trial learning, where it's sort of you stick with an idea as long as it's working for you, and then when it doesn't, then you actually just fall back to your prior. You don't actually carry forward any of the data that you had before. You just resample from the prior. My model actually does compare the new hypothesis against some number of previous trials that it's experienced. So it has a little bit of guided by data. And that calculation is noisy such that sometimes the rule doesn't accurately capture the things that it saw before. So it sort of has some noise in it that sometimes continues to engage with a hypothesis that would be technically ruled out. So we can also apply this model to the recognition task. And so the idea is in that case, the recognition task where you have to just use the rule, you already given the correct rule, so it's you don't have to discover it. But you have to classify 24 test items and count how many A versus B there are, and there's some accuracy associated with it. So the idea is that they're you know the rule, but that your application or evaluation of the rule is noisy. And so with that same probability, you have some probability misfiring the rule or misallocating it. You can basically invest more by trying to avoid that error by checking against more of the examples, basically. So a budget of how many things you check the rule against will influence how accurate you are. And the key idea is that there's no prior bottleneck in the evaluation process because you don't have to think of the rule. So you're given the rule, right? So we've severed the connection between the prior and the thought that the person has because we've given them the thought. They're just about the execution of the thought in that particular case, right? And so every additional item that they check on the test display is going to essentially give them the same fixed benefit, and it has a straightforward cost benefit analysis. So here is a simulation from this model. It's not super aligned with the human data, but I think there's some interesting points to make here. One of them is let's look first at the dashed lines. So the dashed lines are the recognition task, the recognition model. And you can see that as you increase the number of items that you check, your performance gets better, right? So if you apply the rule over and over again correctly, the more of the things that you actually check, you're actually doing the task correctly all the way to the end. And so that you'll get better at the task. And then eventually, after a certain number, you'll hit, there's 24 items on the screen. So you sort of have this linear increase. Now, what you see, though, is that there's a squashing down of the learning curves here. And because the reason is because even though in both simulations they're checking the rule the same way, like if you don't sample the correct rule in the first place, then there's nothing that you can really verify correctly. So even if you have increased capacity for verifying the rule, if you haven't actually generated the rule, then there's like a bottleneck in actually being able to get performance in the task. So what you see there is that like, you can have a situation where you can like show learning is kind of insensitive to the extra computation, basically, whereas this recognition task like shows a scaling phenomena associated with it. And this also shows like diminishing returns for any particular value of the study of the things. You can basically find like where the peak would be of how many evaluation efforts you should actually do. It depends on the cost sensitive, so it'll be dependent on what those parameters actually are. But you can see that like in the model, the resource rational version of this model would check more diligently in the recognition task and actually like be kind of sloppy in the learning task and only consider a couple of examples. It's basically the right thing to do because checking and using a lot more memory is not going to actually help you in that task because of the nature of the task. So the idea here, like if we just like summarize like maybe an implication here is like why incentives don't help discovery. So you can check a proposed hypothesis against more trials, but you can't change exactly what idea was generated. And the model keeps falling back to very simple priors every time it resamples the rule. Like every time it gives up on a rule, it falls back to its prior. And that prior is pretty strong, encouraging the person to always fall back to and start over essentially with a very simple rule in mind and not maintaining a very clear history of that. And so no matter how carefully you evaluate, the correct rule never comes up. You can't really adopt it. And there's a saturation process where you get better at filtering, but there's an accuracy ceiling that's going to be set by the influence of the prior in that case. Incentives do help recognition, though, because you already have the correct rule. The stimuli right in front of you. There's no memory demand in order to kind of retrieve what you saw in previous trials. The only bottleneck there is like how carefully or accurately you apply the rule in that case. And so more effort will lead to more correct items, and then there's no prior update. And so the key contrast that I want to make is like this idea that like learning, the bottleneck is like what kind of comes to mind for the learner, and then checking filters things, but it can't make good ones appear into your mind. Whereas recognition is purely about how many items you evaluate, the rule's known, and so you can directly translate that into accuracy. So just to wrap up, I'm thinking like, I think cognitive science in general in our models, as everybody has been saying, hasn't really, is only beginning to seriously take into account computational costs. And one key feature of cognition that I think is exposed by these kinds of analyses is that it might be an adaptive computation, right? That there's not a fixed architecture, but there's sort of like more cognitive resources that can be allocated depending on the stakes of the problem, where you can allocate more or less, depending on stakes or utility. And some cases, rational trade-offs between effort and reward result in human algorithms that actually deviate from like what might be considered ideal or optimal if you don't account for resource constraints. But identifying what costs are actually applying in a task are not trivial. As I think this example shows, like the kind of standard way of kind of thinking about resource rationality has often been downsampling the hypothesis space or something like that, right? And like you can see here that doesn't actually help explain why you would get these differences. So perhaps generating or sampling from memory is not always where the performance breaks down. Maybe it's in like actually like, keeping a rule in mind and actually applying it faithfully. And maybe another kind of speculation maybe is that the idea generation process is like a little bit more like, I don't know, subconscious or like not volitional in the sense that like, you're thinking of ideas. If they come to mind to you or not, it almost feels like chance sometimes, right? Like whether you like, if you come up with a good idea or not in a meeting with a student or something like that, I'm not sure whether that, like you have much control over whether that actually happens, right? And so the idea might be that might be hard to, a computation that's sort of immune to these kind of cost-benefit trade-offs, whereas other things you can do obviously can be sensitive to those, which is kind of interesting. So yeah, learning discoveries is hard. Maybe creative idea generation is hard. The prior tends to really drive the creative process in a way that's counterproductive to like true discovery in this case. Executing a rule once you know it is more like just an algorithm, and you just have to decide how accurately you want to do it. And the places where resource rationality break down are at least as formative as the places where it works. And I'll stop there and thank all the people that worked on the project.